Hello everyone, the paper I'm going to be talking about is called Non-Gray Month-Long Brightening of KIC 8462852 in the Immediate Aftermath of Deep Dip. This is about the star KIC 8462852, also called Tabby star. It's got a couple other names because it's been sort of the subject of a lot of media attention lately. So this star did come from the Kepler dataset, but it wasn't found as a transit star automatically. What happened was um, there's this thing called Planet Hunters, which is a project where data from Kepler is basically uploaded online, and people, ordinary citizens, can see this data and decide for themselves if certain data from stars looks like it has a transit or not. And that's just because the human eye is very good at spotting these things, and transits are missed with automated algorithms, which include machine learning techniques. And so this star, Tabby star, was spotted in this way. Just because it's got such an interesting light curve, people noticed it and were basically like, what the heck is going on here? And so then it became the subject of all these studies. Now, what this slide is showing is uh, the actual data from Kepler. Now, on the left here, you have the full data from this period of 1600 days or so, where you have a couple of main transit events. Now, there's the one in the middle, which goes pretty far down, and then there's the one over there on the right that goes pretty far down. They both go to about 15 or 20% of the host star's brightness, which is pretty spectacular. It's a pretty big dip in brightness. Now, on the right, those are just some zoom ups of uh, that the transit on the right in those plots, um, where you get some kind of weird transit behavior that looks quite erratic. It doesn't look like any kind of planetary transit thing. The one in the middle of the main plot is somewhat smooth, and then the others are pretty strange. The reason that this got so much attention from the media was because the transit events look pretty crazy, and the dimming factor is pretty large at 15 or 20%. Most planetary transits are a percent or less of the host star's brightness. And so what happened was people hypothesized that there was possibly some kind of alien megastructure being built around this star, called the Dyson sphere. Dyson sphere is just something that surrounds a star and captures the stellar output for use as energy. So it's basically just harvesting the energy. And so that's why this got a lot of attention. People thought, oh, maybe this is a possible explanation, because like how realistically, how do you block so much light with such erratic behavior? Unless obviously there's something like this being built. So the Boyajian et al. Paper, what they do is they obtain some other data, and one of the data sets they obtain is a spectral energy distribution. That's shown in the top right here, and what they conclude from that is that basically there's no significant infrared excess, and which means that there can't be some kind of disk of dust surrounding the star like you'd have in some kind of protostar system that can block all the light that they're seeing. So they can't really explain it that way. What they do is they also image the star with KEC, and you get the excellent spatial resolution with the adaptive optics. Um, and what they find is that there's a very dim small companion star. They're not completely sure whether it's just a visual binary, so the other stars just in front of her or behind it, and they just kind of seem to line up, or if it's a real binary system. But they conclude basically that even if it is a real binary system, there's almost no way these are interacting enough to cause the light dips that we see happening. Um, it's just too far away. What they do is they calculate that it's about 885 astronomical units away from the main star, and that it's probably an M dwarf. And so they decide that there's no way the M dwarf can basically emit enough light or cause any significant orbital effects on the main star to see the light dimming that we do see. Basically, their best guess is that there's some kind of exocomet thing happening in the system where uh, you might have one or multiple exocomets orbiting in eccentric orbits, and they may be breaking up either via maybe some kind of impact thing or some internal process where they have volatiles inside of them and they're breaking apart and they're releasing all kinds of gas and dust, and that is causing a lot of the starlight to be blocked. Now, the Hitchcock paper, what they did was they obtained some data from a couple of telescopes in London. They got some photometry data over the course of over a year, and they were hoping to use that to see what they could glean about the star. So now I'm really talking about methods, and I have to mention this thing called source extractor when you're talking about photometry data because it's pretty ubiquitous. And what the authors of the Hitchcock paper did is they ran a program called source extractor on their images, which basically just automatically calculates the flux distributions for all the sources uh, in the image on the sky, and tells you how bright everything is, whether or not they're overlapping a little bit or what, whether they're circular. So you don't really have to worry about apertures and placing apertures yourself. You can get pretty accurate measurements for all of these things in your image. So one of the reasons that is so important is that when they take the image with the telescope, they actually get other stars in the image, which is good because what they do is they use some of those other stars as reference stars. Basically, stable stars with well-known values for the fluxes that they can use to calibrate their data with. And source extractor allows them to get accurate measurements with their images on what they're getting for the flux of all those other stars. And of course, since what they did was they took photometry data in several different bands, eight different filter bands, um, then it's important to realize that what you do with photometry data is you can see how bright your objects are at different wavelength ranges, basically. And so in the right, on the right there, you can see a graph. The black curve in the graph is uh, something that resembles a typical star spectrum, which is just um, energy density or intensity as a function of wavelength. And what they did was they superposed some filters here just to show what a filter does. So the filters, which are the red, the green, the blue, and the purple curves, is they take the light that's coming from the star and they just let through whatever light is under that filter and block everything else. And so you're just getting light in these certain wavelength ranges that you can use to do science about like what the star is actually doing. You have these different brightnesses at these different wavelength ranges. So each filter sort of represents a different color. Um, you might have a filter in the blue region of the visual spectrum, or the green, or the red, or whatever. Um, and if you compare the images of your star in these different filters, then you can compare in this case, how it's dimming across different filters. So it may be dimming more or less in the blue compared to the red. And that tells you things about what's causing dimming, basically. Now, in order to make the the filter data, the images that they took useful, what they did is they did transformations. Transformation for a filter basically takes your data and transforms it so that it's representative of what you might get if you're using some kind of standard filter. In astronomy, there are certain standard filters that tend to be used a lot, and sometimes your telescope doesn't have those standard filters. But with an array of other data, you can essentially predict what your data would look like with those standard filters. And that allows you to compare it to other people's studies and results, and basically just makes it more universal. So they use filter transformation equations. I won't get into that. It doesn't matter that much. But they also use linear fits a lot in this paper. So that's just linear regression stuff. And this is what they get. Um, these are different colors to represent different filters. These aren't necessarily the filters they use, but they're more the standard filters that they want to use to compare to other people and whatnot. Um, and this just kind of shows qualitatively what the light curves look like as a function of time in these different filters. And what they're showing is that the blue one on the bottom there, um, so you can kind of see there's that gray shaded region, and on the left of the gray shaded region, the blue curve or the blue data is kind of low, and then it starts to rise within that gray shaded region. And the other filters don't really exhibit that same behavior to that degree. And so that's like the first evidence that the star is actually dimming more in that filter, the blue one, which is the B band for blue. It's dimming more than the other filters. And so automatically now, by seeing that, we know that somehow whatever is blocking the light is absorbing more of the blue light than the red light. Now what they did was they focused on that gray shaded region in the plot at the left here. What the authors say is that represents a region in time where the star is coming out of a dimming event that we sort of missed the main part of because there's a gap of data to the left of that region, but we're getting the egress portion of the transit. And what they do with the data is they plot the magnitudes in different filters against each other. And so the graph at the right is one example of that. Basically, what's happening is that as we move forward in time from the beginning of that window, the star is getting brighter and the magnitudes are therefore getting smaller. So say we start at the top right of the graph at the right there. That top right point, the B band magnitude is around 12.45. As we move forward in time, what's happening is that that is getting smaller. So we're moving down to the left. At the same time, your V band magnitude is getting smaller because we're getting brighter in both bands. Um, but they're not getting brighter at the same rate. So there's some slope associated with the linear fit that they show there. And that slope tells you the relative rates at which these are changing brightness, which tells you the relative extinctions for this transit event, basically. And they do this for all of the bands, or at least four of the bands uh, that they have good data on. And so they calculate these slopes for each band, where the slope represents the attenuation ratio. So AB over AV is just the attenuation in the B band over the attenuation in the V band. Um, and then they say that this is equivalent with a couple of assumptions to something called the optical depth ratio, which is the tau lambda over tau lambda V that you see in the equation there. And then in the equation, there's also a lambda and a lambda sub V. That's just the wavelength of the center of the visual band, and then the other lambda on top is the wavelength of the different band that you're comparing to. So they're comparing all of these bands or filters with respect to the visual one. It's just a way to normalize them to be consistent, basically. Um, and you see there's a parameter alpha. So the lambda over the lambda sub v is raised to the negative alpha. And if you have these optical depth ratios or attenuation ratios, um, and you know the lambdas, then you can do another fit and calculate what this alpha is. And this alpha is sort of representative of the color dependency of these dipping events or these attenuation events. And so what happens is a higher alpha is associated with more color dependency. So the blue light is basically absorbed more and more than the red light at higher and higher alphas. And then as alpha gets lower, it becomes something called color neutral or gray. So as alpha goes closer to 1, it's considered more color neutral, and that just says that there isn't this strong dependency of like blue light being absorbed or blocked a lot more than the red light anymore. This alpha value is important because it's been calculated in several other studies of the star, of Tabby star, in the literature. Um, and people have found several different things. Other people have found values closer to 1, which is more color neutral. Uh, a lot of them are around 1.1 or so. Um, Here, the value is around 1.33. So there is some discrepancy, and the authors of this paper, the Hitchcock et al. Paper, point that out. And they also point out that their error bars are pretty big. So they have 1.33 plus 0.43. And the other papers are giving alphas around 1.1 or so. And so all that is included, it's within the 1 sigma error bar, basically. Um, and so it's a fair point to say that the errors are just too big to really say for sure that this is color neutral or has a high color dependency. In this paper, they argue that uh, it's got a high color dependency, thus the non-gray part of the title of the paper. Um, Whether that's actually true, I think that needs some more studies to back it up. Now, one pretty important um, result that you can take away from the alphas are that you may have a lot of small dust grains in the system, basically. A lot of the absorption could be caused by dust. Um, and that's evidenced by the fact that we have these color dependencies. Um, the fact that we're seeing more of the blue light being absorbed than uh, or blocked than the red light matches up with what you might expect from submicron dust particles. Um, The reason they have to be submicron is just because you have to have a small enough particle to where the diameter of the particle is similar to the wavelength of light. So in me scattering, which is the full solution to the Maxwell equations, um, you so what happens is once your particle size and your wavelength become similar, you start running into these effects that you ultimately really see in Rayleigh scattering. And Rayleigh scattering is an approximation to me scattering, where you get this closed form solution that says you have this 1 over lambda uh, to a high power dependency. Um, and so all this basically says is that if you have submicron dust particles, then the diameter is less than 1,000 nanometers. And the wavelengths of light we're talking about in these filters is, around 4 to 700 nanometers. And so the diameter of the particle and the wavelength are becoming similar now, and you start running into that lambda dependency that really comes out in Rayleigh scattering. Um, and so you scatter the blue light more than the red light, which is exactly what happens in our atmosphere. That's why the red light tends to come straight through, and the blue light gets scattered around, and so we lose the blue light when we're looking straight at the object, but we see it elsewhere. And they suggest that's what's happening here. That's why we get that color dependency that they claim with the alpha of about 1.3 or so. So whether that's what's actually happening, we have a bunch of dust grains in the system, is hard to say. If anything, it gets a little confusing because then you might expect that we would see infrared excess, um, which we don't. And also, what happens is when you have dust particles that are that small, they get blown away by the radiation pressure of the star. And so the authors in the Hitchcock paper do say that you need some source to replenish that dust continuously, basically, especially on the scales that we're talking about. And so, like I said, it starts getting a little hazy. It's not really clear what's going on. The dust seems like one of the most promising explanations, but it's definitely far from satisfactory. And so, just as one final discussion, I want to show this plot here. This plot is from Boryagin et al. 2018, so a slightly newer study from their 2016 paper. And what they do is they compile data from the past 130 years or so to show that the light from the star, from Tabby's star, has been steadily getting lower and lower. So it's been decreasing, dimming over the past 130 years, and so I think that's pretty interesting. So we're seeing this short-term, very erratic behavior from the star, as well as this long-term trend here. So it's overall just pretty interesting. No one really knows what's happening. I think it's going to take a lot more to figure out what's going on in the system. And so far, the data has been pretty inconclusive with even just a color dependency of the absorption. So it may not be something as exciting as uh, an alien civilization building a Dyson sphere around a star, but I think it's still a pretty interesting and worthwhile topic.